Hey grade 12 learners, welcome to this explainer. Look, if you've ever stared at the electrochemistry chapter in your textbook and just felt totally overwhelmed by the massive wall of definitions, you are absolutely not alone. Today, we're going to take those dry textbook terms and translate them into a dynamic, intuitive system, one that's actually easy to visualize and, more importantly, super easy to memorize for your board exams. We're essentially going to turn invisible ions into something you can easily picture in your mind's eye. Let's get started.
Okay, here's a quick look at our roadmap. Today we're covering 1. The basics of conductivity, 2. Understanding molar conductivity, 3. The ultimate limiting value, 4. Strong versus weak electrolytes, and 5. Your exam day takeaways. Let's dive right in. All right, Section 1, the basics of conductivity, the foundation of electrolytic flow. So let's start with the absolute baseline concept, which is the physical environment of our chemical solution. Now, the standard definition sounds incredibly technical, right? But let's break it down using a real-world analogy. Think of conductivity like counting all the moving cars in one specific, rigid square mile of a busy downtown city. In this scenario, the electrodes are kind of like toll booths that set the boundaries of our city block. They have a unit cross-sectional area and sit exactly a unit distance apart. We are only looking at the electrical flow, or the traffic, within a strict, fixed volume of liquid. So if you pour in more water to dilute the solution, the number of cars inside that specific square mile actually drops because they spread out to other parts of the city. That rigid, non-negotiable boundary, that's exactly what defines standard conductivity. Moving on to Section 2, understanding molar conductivity, tracking a specific fleet. Now, here is where we completely flip the script. Instead of watching a random fixed block of the city, molar conductivity means we're tracking exactly 1 mole of ions. Think of this as a very specific pre-assigned fleet of vehicles. We literally don't care about the boundaries of the city block anymore. We're just following this exact fleet to see how well they conduct electricity as the overall city limits expand through dilution. If you add more water, the volume of the solution increases, but our focus stays totally locked onto that single designated mole of electrolyte. And because the space gets larger, the ions get further apart. They actually experience less friction and less attraction to one another, which means they can move a whole lot faster. So that really begs the question, what happens to our fleet of ions if we just keep widening the roads and expanding the city indefinitely? If a little extra water gives them more room to move and boost their conducting power, what's the absolute ceiling to this effect?
Which brings us to Section 3, the ultimate limiting value, reaching infinite dilution.
This little thought experiment brings us to the absolute theoretical limit of our mathematical scaffold, which is limiting molar conductivity. This is exactly what happens when concentration approaches zero, otherwise known as infinite dilution. Going back to our traffic analogy, this is the maximum possible speed and flow our specific fleet of ions can hit when the roads are completely, perfectly empty. There's just so much water, so much open space, that the ions literally cannot even feel the presence of the other ions. The traffic is zero. Interionic friction is entirely gone. They're driving at their absolute maximum potential, and that gives us the limiting molar conductivity.
Next up, Section 4, strong versus weak electrolytes, how different vehicles handle open roads.
Let's see how all of this builds when we compare exactly who is driving these vehicles as the roads get wider. Because, not all electrolytes respond to an open road the exact same way. Strong electrolytes are basically like high-end, pre-assembled sports cars. The second you drop them into the water, they almost completely dissociate into ions immediately. Since they're already fully functioning cars, giving them more open road through dilution only increases their molar conductivity slowly and gradually. They were already moving pretty well. But weak electrolytes? Man, they are fascinating. They're more like scattered car parts. Initially, they only partially dissociate. But the moment you give them extra space through dilution, it's honestly like magic. Those bound molecules suddenly snap apart, assembling into thousands of new, zooming vehicles right on the spot. So their molar conductivity increases sharply as you add water. And as you can see, the visual data backs this up perfectly. When we look at the spike in molar conductivity upon extreme dilution, we see 2 totally different behaviors. When the concentration drops towards zero, a strong electrolyte barely changes its conducting power. It's just a minor little bump. But a weak electrolyte, it experiences this massive, towering spike. It just skyrockets. And that's because all those previously inactive bound molecules finally have the space to snap apart into free-flowing electricity-conducting ions. The empty road literally creates more cars. Finally, Section 5, your exam day takeaways, the quick study guide. To make sure you absolutely crush your upcoming board exams, let's lock down these critical differences. Grab a mental screenshot of this checklist. First, remember the fundamental shift. Conductivity is about the conductance of a fixed volume, a rigid city block. Molar conductivity shifts the focus to exactly 1 mole of ions, our specific fleet. Limiting molar conductivity is the maximum conductance at infinite dilution, when those roads are completely empty. And finally, never forget the behavior difference. Strong electrolytes show a gradual increase with dilution, while weak electrolytes exhibit that steep, massive spike when they hit infinite dilution. Burn those distinctions into your memory for sure. As you dive back into your textbooks, consider this final, provocative thought. How do these exact rules governing infinite dilution, chemical dissociation, and invisible ionic traffic jams dictate the lifespan and power of the smartphone battery you're probably relying on right now? Electrochemistry isn't just a chapter in a textbook, it's literally the hidden engine driving the modern world. Keep that in mind as you study, and you'll really start to see the magic in the mathematics. Thanks for joining me on this explainer, and happy studying.